introduce the concept of motion planning, and it will be a short lecture starting with some demonstration, and then just to introduce you some basic concepts of motion planning without going into too much depth of individual topics, which will be covered in subsequent lectures. So first, we will start with 3 demonstration videos. Why 3? Because we will start with a fixed base bot video. Second, we will show you a moving bot video. Finally, a flying or drone video. So they will look at different applications and use some concept of motion planning or object detection, which is very much part of motion planning. All these 3 videos has subtitles and voiceover. So let us first look at these 3 videos, and then we will jump into the some introductory theoretical concepts. So this video, before I start running, is about a fixed base bot, the title suggests. And we developed this fixed base bot for a set of children who have severe speech and motor impairment. We were trying to help them to do fabric printing task with a robot. So in this video, we'll not go into detail of the application. Rather, we will show that how we compare 2 motion planning algorithm. And one is a very naive one, just avoiding obstacle. Another one is a bit more sophisticated one using value iteration algorithm, and how we compared them and also tested them with actual user. So here we go.
This video presents our work on gaze-controlled, safe human-robot interaction for users with severe speech and motor impairment. Here we have presented a safety algorithm which tracks and avoids human hand and other obstacles in the robot workspace while planning the trajectory of the robot. We have started by simulating a generic human-robot interaction environment involving a tabletop robotic arm on ROS Gazebo simulation. The robot executes a safe, intelligent trajectory around the hand based on workout decision processes if the hand is intersecting the default linear path to the target as shown in the upper left window. Upper right window shows a motion capture scene from the OptiTrack camera setup. This video shows a targeted user with severe speech and motor impairment operating the proposed human-robot interaction system for a reachability task. The user is instructing the robot through the in-house developed webcam-based eye tracker and the 4-way control on the live video see-through user interface.
So as the short video showed that here we mainly compared one algorithm which was just avoiding the hand obstacles, another one using Markov decision process. What is Markov decision process? Value iteration we will discuss in future lecture to avoid any occurrences of the palm on the table. And also you may heard of this OptiTrack Flex 13 system, which we have also used to validate the algorithm with respect to accurate tracking of both robotic end effector as well as the human hand. Next, we will look at one ground moving bot for a warehouse simulation application. So here we go, and here you will see that we developed a warehouse simulation using Microsoft HoloLens. So it has applications mainly in developing task scheduling algorithms that we can discuss in future lectures. But in this case, you will see the ground moving bot is avoiding both virtual and physical obstacles. So what is virtual obstacles? That is a obstacle rendered using the HoloLens, using holograms to pretend a warehouse situation, as well as the physical obstacles that were some objects which are actually placed on ground. So here we go.
This video, we are going to demonstrate virtual obstacle avoidance and heterogeneous multi-robot coordination in mixed reality with a human in the loop. This video demonstration consists of 2 components, virtual obstacle avoidance and heterogeneous multi-robot collaboration. We have a mixed reality interface which emulates warehouse type of scenario. There are virtual obstacles present in the scene as well as real obstacles. There are virtual buttons when pressed act as inputs to the robots. And when it comes to heterogeneous multi-robot collaboration, we have two kinds of robots, mobile robot and fixed based robot. When the user press any button, both the robots have to coordinate in a way that the orange colored load is being picked and placed. The mixed reality interface emulates a warehouse kind of scenario augmented on the real world as 3D holograms. There are two fixed based robots and hence there are two buttons that follow the user. Each button represents a command to the mobile robot to go towards a particular fixed based station. When the user pressed the button, the robot is going towards one fixed base station while avoiding the virtual obstacles present in the scene. It can be observed that these virtual obstacles are not present in the real footage in the top right corner. The robot is also observed to avoid the real obstacle in the scene while going towards the fixed based robot. The mobile robot uses ROS-based navigation architecture with A-star algorithm and dynamic window approach as global and local planners. As the mobile robot reached into the workspace of the fixed base station, the load which was carried need to be pick and placed. The load is detected by the camera mounted on the top of the fixed base robot and uses classical computer vision technique to determine its position in the scene. Thereby, we achieve multi-robot collaboration in a mixed reality via a human in the loop.
So you will see some similar demonstration of this later on. And also we will demonstrate a situation where multiple fixed base bot are sharing a workspace. We published about the work in this year's Roman conference. But presently we will move on from ground to that we will fly and we will go to a flying bot. So in this particular example, we did not use concept of motion planning as such. Rather, we concentrate more on localizing a low-cost drone using computer vision algorithms, as well as we worked on developing manipulator for picking and dropping object from a drone. So here you can see a big drone and something is hanging from it, which is designed in our lab. But we also developed a test environment to compare alternative modalities of interaction for operating drone manipulators. So here we go.
This work presents a novel approach to simplify aerial manipulation by leveraging natural modalities for improving human drone manipulator team. In this demonstration, the left video showcases the drone manipulator system in action. Top right corner highlights the manipulator's movements controlled through speech, while the bottom right corner demonstrates the same movements using eye gaze control. As part of testing the human-machine interaction, we propose a novel mixed reality-based human-drone interface utilizing low-cost nano-drones and a customized computer vision pipeline to localize the drone from the scene camera feed of an MR headset. The overall framework along with the testbeds are shown in the right figure. In this testbed, the user drives the drone toward a fixed target and selects a virtual icon corresponding to the target icon. The user performs this selection 4 times for 4 different targets. The user's performance is compared with a simpler testbed shown next. Here, the user performs multiple virtual sphere selections while hovering near the target. 16 users with an average age of 24 years with no prior knowledge of drone piloting or MR interface participated in the experiment. It shows that speech proved to be more precise and consistent for tasks requiring stable drone control, and eye gaze offered speed advantages in simpler task execution. The contributions concerning human drone manipulator team are as follows: in aerial manipulator part, in human drone interface part, in assistance.
Right. So next, after these demonstrations, where we looked at all three conditions: fixed base bot, ground moving bot, and flying bot. Of course, they in future they can also collaborate with each other in a grand plan of collaborative robotics. But mainly, I try to give you the set of applications or immediate applications where we can use this motion planning algorithm. Of course, we can go beyond to many other applications like game playing or applications in economics, even in UI UX design, where we can use similar concepts. But of course, these algorithms are often easier to explain, or the motion planning algorithms, they are easier to explain when we can see something is physically moving, and we will use this analogy as we will move along.
This work
So the first difference in concept when we learn motion planning algorithm is in terms of knowledge representation. So earlier when we discussed supervised, unsupervised learning, that we start with a data table where we have multiple columns we called features, and then we have rows where we have the data, and often the last column was our prediction column for supervised learning case. And why I am repeating this, because you will see that in many cases, we convert a motion planning problem into a supervised learning problem. One good example is this DeepQ learning, where we, or direct utility estimation in reinforcement learning, where we estimate a parameter called utility using supervised learning. But coming back, in most motion planning algorithm, we represent knowledge in the form of a graph or tree. What is a graph? That a graph consists of two vertex and edges. Visually, that we represent the vertex like these circles. And you may imagine that these are waypoints, like as if when you are, say, taking a flight from Bangalore to, say, somewhere, Delhi or etc. So the flight will go through a set of waypoints, although you are only aware of the source and destination, but during flying, it will go through these aerial waypoints. So you can consider them as waypoints. In the previous examples, these waypoints are maybe obstacles or intermediate locations, etc. And the permissible paths, often that one waypoint may not be accessible from another waypoints, that we use these edges to indicate that which waypoint is accessible from which other points, like this. In some cases, these edges may also have direction. That means this waypoint only accessible in this left to right direction, or maybe down, up to down direction, like that. And we, in graph theoretic term, we call this directed term. In some cases, we can further simplify this problem, that instead of discussing these waypoints and graph, we just discuss a grid. So this is not same as a data table. And the grid looks like that, where each grid you can consider as an waypoint, as if these are the waypoints. And for simplifying purpose, we only consider the agent can go like this. So some algorithms, like, say, when we discuss about value or policy iteration algorithm, or even if we get time, we will discuss also about basic reinforcement learning. Those algorithms we will discuss in the form of this grid-based movement. And when you get the so this ground moving bot, so many times we imagine, or we represent the floor as a set of grid, because the robot can only move up, down, left, right, hood of robot. And that way we can simplify our calculation. So the difference from previous algorithms to this set of algorithms, that we will not talk about a data table, we will talk about a graph. Many times we give names, like we can start with abstract name like A, B, C, D, etc. to distinguish these nodes from others. or we will talk about this graph, or we will talk about a grid-based structure and moving in the grid. But again, to remind you that this graph or grid, it not necessarily, it does not necessarily mean a Euclidean space and physical movement. We can also use them to represent states, internal states of a system, like someone is playing chess, or even we are used it in a particular application where we are designing a user interface, and different state of the user interface we represented by these nodes and graph. So this has far-reaching applicability, but just for ease of understanding or immediate applications, we consider that these are physical waypoints and physical movement happens through these edges. So what is the aim of motion planning? Why we learn motion planning? So first is we try to find the best path or route. I think it does not require much explanation. You hire a Uber or Ola and you wanted to reach your destination as fast possible. And there are many constraints on the way: traffic jam, condition of road, of course, distance, the primary constraint, etc. And you wanted to reach your home as quick as possible. So what is the best path or route? Now, whenever we are taking best path, best route, we talk about optimal path. And optimal path, it's also a bit funny term that what we are optimizing. That means that I kept it open question, that optimal with respect to what? So for example, just as I told, it can be optimal with respect to the distance. But as you know, often considering the Bangalore traffic, that many times we avoid the shortest distance path because if it goes through the city, there will be too much traffic jam. So we will take the outer ring road, because even though the distance is higher, we will reach our destination quicker due to less traffic. So in that case, we are trying to optimize the time of travel. When you are flying, there are some other factors, like you may heard of this headwind, tailwind, etc., which headwind is wind opposite to the direction of movement. Tailwind is which is pushing the flight towards, that means towards the direction of movement. And the result is maybe we are trying to optimize the fuel consumption, because if I choose a route where I will get tailwind, it will push the flight to forward, consuming less fuel, even though that may take through a higher distance. Okay, and another interesting thing you will see in a later lecture, that often when I am developing an algorithm and I am talking about optimality, we often talk optimality with respect to a closed world assumption. What is closed world assumption? That it is a common concept in many AI algorithms, that what is known to the agent, and it is trying to optimize within this known knowledge. And if new knowledge comes in, then may not be the previous algorithm that we taught you as this optimal algorithm and giving optimal path. You can find a better algorithm maybe. And we will see such an example later on during reinforcement learning. Next is that it's not only optimal solution, but also finding the solution in finite time. So many times your surrounding or environment change, and like the robot example, you say your warehouse simulation example, that the warehouse configuration may change, and you want to get the solution in finite time and space. So you will learn some term called completeness, that when I will talk about multiple algorithms doing the same thing, of course, we need some criteria to compare the algorithms. So the first or most important criteria is, we will term it as completeness, whether the algorithm actually terminates. What do we mean by termination? That it will give you a result. The first question is whether the algorithm will give you a result, whatever the time, space, etc. Next is space complexity, that how much here space means not like our state space, but the space means the memory space. And you will find there are some fantastic algorithms, like we already mentioned one called A-star in terms of global planning. And A-star algorithm has every good properties, but its space requirement is exponential. That means for larger space or larger state space, or just when you are using it for a motion planning in a large area, the A-star algorithm needs so much memory space that you get the indication in terms of that your computer hang, that it's running and it's not giving result. So how much computer memory space the algorithm takes to run, and then time complexity, how much time it takes. And many times the problem you will see that the algorithms is giving you or guaranteeing you, mathematically guaranteeing you to give optimal results, but its time and space complexity is too high. And that's why we many times go for something like compromise on the respect to optimality and try to get an algorithm which can give me quick solution. Third is the amount of information required. And when we teach motion planning, we can start with very basic data structure algorithm that we will see in next slide, like breadth first search, depth first search, etc. And then we can move on to more sophisticated algorithm up to the reinforcement learning, even model-free reinforcement learning. In some cases that we need much less information, rather the agent, it learns by making a movement. So there will be some algorithms you will see where we need to know the whole environment in the form of all the waypoints, distance between the waypoints, even sometimes something like a heuristic knowledge, etc. On the contrary, there will be algorithm where the agent will only get an indication that how far he is from the goal now. And that is good enough. And based on that, it will do this motion planning. So in most of the algorithm, we will teach in class that we at least know the start and destination, that where it is starting and where it is ending. And another important feature it knows, which maybe I will know, the agent knows, sorry, I'm trying to handwrite, knows where it is. So when the agent make a movement, it know where it is. And it may sound a bit funny or trivial to you, but then there is a class of algorithm like something called partially observable MDP, where even relax this requirement also. The knowledge agent may not exactly know where it is. You can just imagine that you are walking through a new city. So in algorithms like Dijkstra's algorithm, Bellman-Ford or Bellman-Ford all-pair shortest path algorithm, even in case of A-star, we know or we take the distance among waypoints or nodes as input. Although in some future algorithms, you will see that this information is not required. And then we will talk about some terms called heuristics, reward, utility. So they all have, they relax this requirement of knowledge, or the heuristics, they often help you to visit less number of nodes, or means that you have to explore less space within the whole state space compared to uninformed search. And reward utility, reward is giving you an indication how far you is from the goal node. Utility is termed long-term reward. So we will learn about this term as we go along. So let us now look at the basic concept where these terms make some sense. So when we also teach the motion planning course in next semester, we divide it into mainly two spaces. So you can classify motion planning algorithms in many different ways based on the knowledge requirement, like as I was telling, uninformed and informed search, then Markov decision process, reinforcement learning, etc. Based on the type of the algorithm, you can make a classification based on global planning and local planning. Global planning means that you are going from, say, IISc to Electronic City. That global planning is the what the Google is showing you on the Google map, the road you choose. Local planning is that you are driving your car and then there are another car or vehicle coming or a motorbike is coming on your wrong way. So in the local stage, how you will avoid collision, etc. However, when we talk about the approach of solving motion planning problem, we classify motion planning approach based on this knowledge representation, which we just talked in the previous slide. And we classify them as in motion planning in discrete space and motion planning in continuous space. And discrete space motion planning is we discretize the state space. This often or most commonly being used for fixed base or mobile bots, which moves only on a 2D plane. And then we will also briefly talk about motion planning in continuous space, which we mostly used for drone motion planning or in a 3D space. But you can also use continuous motion planning. I will show you example for fixed base bots as well. And as we will come to an end, you will see the advantage and disadvantage of both approaches. So for discrete motion planning, we have to learn this very concept of state space search and what is states and what is space. So this is also taught in the domain of control theories, that a state is something like, as the name suggests, that this is a state of a system, like a configuration of a pieces of a configuration in a game, like the positions of the chess pieces on the chessboard, the position of a mobile bot at a particular point in the ground. These are all we can define as states. And state space is the all possible states, like say for chess, all possible valid position of the chess pieces on the board. That can be a state space. And as you may see, that's the state space in many practical problems, the state space can be infinitely big, like in case of chess, or in many of our practical problems, we can confine the state space by the working envelope of the robot. That say for a fixed base bot, the robot can go up to a certain circumference, and we define that area as our state space. Or if I have a mobile bot, I can let it run within a fixed area, say within the classroom, within a warehouse, or within a particular area of the city, etc. And that is our state space. And then we move from one state to another state that we term as the state transition. And we try to find the sequence of state transitions, which will be optimal with respect to something that we term as our optimal. So when we define a state space model, we define as initial state where the agent is starting to move or where I am starting the game of chess, the initial position. Then we define a set of operators. In our case, for robot path planning, the operators are the allowed movement of the robots. Although it is easy to say the allowed movements, but later you will learn about something called holonomic constraints. For example, when you are parking a car, you cannot move the car sideways. So you have constraint in terms of movement of the bot as well. So considering all possible constraints, what are the possible way of state transitions? That is the operators. So just wait for 1 second. Just guys, just for 1 second. Sorry, guys. Disturbance. Next, we know a goal predicate or goal node. In most of the algorithm, you will see that one of the circles or one of the grid position I will mark in green or a gray and tell this is my goal node. We want the agent to go there, and many times it works as a termination condition that once the agent reaches the goal nodes, the algorithm ends, that I am successful to finding a path. However, in many cases, we will use some sort of rule or formula to find that whether the agent achieves its goal. Like, for example, in a game, like in a chess, the checkmate condition will give me the goal predicate. And the optionals are cost of operation and cost of solution. So cost of operations operators is often that we marked as a real number on the edge that I am moving from one state to another state, how much it will cost. So for motion planning, it is often obvious that the distance is the obvious choice. We can put up something else like the time needs or fuel consumption, etc. Cost of solution is that many times in a case that you can reach a destination using multiple paths, maybe with respect to your cost of operator, both of them can be optimal path, but we can also have other criteria to determine the cost of solution. Maybe we can have multiple solutions. So we can use the cost of solutions to compare the or decide the best solution. So this is one example of uninformed search. What is uninformed? That I only need the state space, that the definition of states and the transitions, and from that I find a way to reach different nodes or browse through the nodes. So you can just imagine that these are a set of waypoints within Bangalore city, and I am trying to design a travel route that where we will go through all the visiting points within the Bangalore city limit. Say maybe we are starting from A, and you can see that the breadth first search works like this. It's already there that from the A node, I will reach all the nodes that I can first reach from A. So like this. And then I select one of the nodes, say B, and from B again, I traverse all the nodes that I am allowed to travel from B. Then I go to C node and I see that only from C I can reach D, and already I travel D. So next I will go to the G node, and from that I can travel to E. And from E I can travel to F and H. So like this. So from a particular node, I travel all possible nodes that we can reach from that node. And you can see that from a graph, I got a tree structure. What is a tree? A directed acyclic graph, that is the definition. That from this structure, I can get a sequence of nodes that I will visit following the breadth first search. An alternative technique is depth first search, where we will just follow one single path till I come to the end. So but we will discuss depth first search maybe in the next slide. So this is, I'm just giving you as one example of ununiform search. And one example of informed search is A-star search, which is very commonly used. In the warehouse simulation video, we use this as a global planner. So in A-star search, what we do, that we use the distance among the nodes, plus we use a heuristic, which gives me a straight line distance from the goal node. Why we do so? You may heard of, or later you will learn about something called Dijkstra or Bellman-Ford shortest path algorithm, that which can also give me shortest path from in a graph, which will minimize the distance among nodes. But using these heuristics, we can travel from source to destination by exploring far less amount of nodes than a Dijkstra search type of algorithm. And that makes A-star is very powerful. And then we can mathematically prove that with certain constraint on this heuristic, this A-star search gives us optimal path. But it has exponential space and time complexity. So without going into too much technical details at this point, you can remember that in A-star search, we call it informed search, because here we use something called heuristics, which give me an indication that how far I am from the goal. And the reason for using this heuristic to reduce the number of visiting the number of waypoints or nodes when I am trying to find the shortest distance between a pair of nodes. Okay, so for the time being, you take away this knowledge. Later, we can talk more details about the A-star search itself. And in BFS, we do not need any extra information. We just follow the links from the nodes. While in A-star search, we use the information in the form of distance among nodes as well as a heuristic from the goal node. So this is about sequential decision problems that this Markov decision process that were a classification of different types of planning algorithms. And in particular, we will discuss about this Markov decision problems and the value and policy iteration algorithms later on, which will set up the ground for further discussing the reinforcement learning problem. And we will also learn about this concept of utility, etc. But for the time being, when we are talking about state space search, you can see the basic difference that one is that where we have explicit action and sub goals, and there we have a planning algorithms, like you may all heard about project planning. So there are different planning like partial order planning, graph-based planning, set of algorithms are there. And when the actions and sub goals are not explicit or they are stochastic, there is some uncertainty due to the inaccurate sensing or some inaccuracy maybe in the inverse kinematics of the robot, that it may not reach the exact location it wants to be. We have this uncertainty, and there we use this Markov decision process based algorithms. Okay, so just let us move on. And next, we will very briefly discuss about this motion planning in this clear hat. So motion planning in continuous space, it turns out to be a bit more complex because we are talking about a continuous space, and discretization always make the problem easy, maybe at the loss of some information. And we will learn the concept of configuration space. So I may mention this term a few times last week. So here what we do, that it's a transformation from physical space in which a robot exists to another space of higher dimension, where we treat the robot as a point. In this space, the configuration space is defined on by considering all the degrees of freedom of the robots, and like what it's not only, say, when we are so far we are talking, if you look if you think a bit, that we are mostly talking about translation type of motion, that the fixed base bots end effector is moving from one space to other, and I can see the space and see the end effector is moving. But what about that it's not moving from one space to another, but it's rotating? So the configuration space is defined considering all possible configuration of the robot, and any particular configuration of the robot considering both translation or rotation can be represented by a single point. So this is not easy to get on the very first go, but I will show you some examples. Probably it will make it clearer. And of course, we will use some more abstract concept of space, which we often may not be able to visualize. So in case of discrete planning, we can visualize the space that it's on a floor, it's on air. But often in configuration space, we will go beyond the 3 dimensions. And that's why it's not easy to visualize, which makes it further difficult to understand. And anytime the utility of the configuration space is that if I can define a free path from one point to another, that solves my motion planning problem, considering both the translation and rotation constraint of robot, considering also any obstacles on its way. So in this context, we will also define this space called task space and workspace. Basically, the task space is to control the position of the tip of a marker or the end effector, that where it can move, very similar to our state space, that which we can visualize. And workspace is a specification of the configuration that end effector of the robot can reach. And the task space is often defined with respect to a single task, while the workspace is what is allowed but all possible tasks. Okay. So I put the more text on the slide so you can also read it. So this is, for example, one configuration space of this simple 2-link robot. So yeah, you can see that it's a 2 DOF, that there are two links, and this is the two angles it can move. Okay, and two link structure. And the configuration space is defined by these two angles, Q1 and Q2. So any point on the configuration space is a specific angle of this Q1 and Q2, because these are the two free parameters the robot can move, and we fix the base that it is not moving anywhere. It's a fixed base bot. And within this space defined by Q1 and Q2, the robot can only this XY, the end effector of the robot, can only, if we consider all possible movement of the robot within the link structure defined by L1 and L2, it can only move within this torus structure. How it does so, that we'll not bother about proving right now. So you can consider take it granted. But this torus is showing all possible spaces this X and Y, this end effector can go. And the radius, the outer radius, maybe I will use a pen, and this outer radius and inner radius, these are defined by the link length L1 and L2. So this will be L1 plus L2. This will be the shorter linkage length. So the torus will be defined by the length of the linkage arms, and the shape will be defined by the robot structure, that in this case it's a torus. And any motion planning problem will be defined by drawing a line within this torus, which will bring the robot from one configuration of this Q1, Q2 to another configuration of, say, Q1 dash, Q2 dash. And if my algorithm can define this path, that how I can move from one Q1, Q2 to another Q1 dash, Q2 dash, my motion planning problem will be solved. So these are some more examples of similar configuration space defined for fixed base bots. And in particular here, you can see that this claw-like end effector create this claw-like structure here in the configuration space. That what are the possible position? The white region is the free space where the robot can move. And same thing on the other two picture. And also it's showing the all possible position of the robot end effector in physical space and the manifestation in the configuration space. And this gray region is something that the robot cannot reach due to this thing. And this is represented like this in the configuration space, which is defined by the angles of the robot in this case. Okay. So this is from fixed base bot, we can move to the example of a configuration space of a mobile bot. So this is the workspace, and there is an obstacle on the top left corner. You can see in this picture here. And this is represented by this parallelepiped here in the configuration space, that here the robot cannot go. And similarly, if the obstacle is of circular structure, considering the translation of the robot, it will be something like this inclined cylinder. So of course, this is not defined arbitrarily. So there are a way of doing that. There is a specific chapter or lecture or session on obstacle representation in configuration space. So where for simple obstacles, we can use geometries to represent that. For more complex obstacle, it become more complex. And on Thursday, we will discuss about some algorithm called sampling-based algorithm, where we need not to explicitly write equations of the cylinder or parallelepiped here. Rather, we will use some sampling strategy to only know that whether a robot can go to a particular point in the configuration space or cannot go. So how do we plan motion in configuration space? In the discrete space, we have all these VFS, DFS, Esther algorithm. We can also use similar algorithm in configuration space. What we can do is that we can first define the configuration space, as you saw in the previous slide. And now this configuration space we can discretize and use our discrete space algorithm. So when we'll discuss the algorithms in the discrete space. Mostly we'll discretize the workspace and then we'll explain because it's here to visualize. But what we can also do that we can also discretize a configuration space, which is a higher dimensional space, because mathematics need not to visualize. Humans have to visualize. Mathematics need not to visualize. So the same algorithm which is working in 2D, it can be extended to a higher dimensional space. So the same A star or any other algorithm, we can also use in configuration space by discretize the configuration space. But in more generic term, this is the how we define or how we plan motion in continuous space, that we define the space with one dimension per robot motion or pose or each DOF, map robot to a point in the space considering all the possible DOF or pose or position of the robot, and we define its configuration space, and we represent all obstacles in the configuration space as you saw in the previous slides examples. Then motion planning is usually done in three steps. We first define the configuration space. We often discretize the configuration space, although it's not mandatory. We also will discuss about sampling-based approaches where we need not to define the C explicitly. Rather, we will just probe the C to know that whether it is free space or not. But here we can search C, and every planning problem may have a different definition of C. So these are different way that we can define the configuration space of a mobile bot using the X, Y, and theta, or using in a dynamic environment taking also the time and velocity, etc. So we can define the configuration space based on also our requirement. But in general, what we do that in the configuration space, we represent the pose and position by 1 point, and also we represent the final desired position and pose of the robot by another point, and try to find a set of points within the free space where the robot can go within the configuration space, and that gives us the sequence of position and pose which the robot can follow to reach the final desired position. So anyway, in this is just an introduction to the motion planning problem. So here, what we can we learn the very basic concepts of motion planning and the two classification in discrete and continuous space. We learned this term of state space search, how we represent state, the concept of uninformed and informed search, although very briefly. Just we take the example of breadth first search and A-star algorithm. We learned the very basic concept of configuration space, where we define a higher dimensional space considering all the degrees of freedom of a robotic agent, and how we define a motion planning problem in configuration space. We did not go for the solution or a specific algorithm to do motion planning in configuration space. We introduce the concept of that. What does it mean by plan motion in a configuration space? So with that, we'll stop this session. I will stop sharing, and also I will stop recording. Yeah.